I'm Ankit. I'm happy to present some of the recent work that we did to enable Pinot joins at scale for a production use case internally. So as you might know, like joins is a recent feature that was added to Pinot. Before that, we didn't support joins. And yeah, it was a journey to make it happen. We launched it for a big use case internally recently. And this talk will just cover about like how our journey was and where we go from here. So just for context, this was a big internal marketing use case that we had. For those of you who know, like there is a term called cohorting. Like I didn't know about this before the use case, but that basically means that you have a set of users. So let's say all Uber users, and you have a set of attributes for them. So let's say you're looking at users who have taken a trip in the last 60 days or so, who are a part of Uber One membership, which you should join, by the way. And who are in particular city ID, and you want to send a particular kind of marketing campaign to them, then you are interested in like getting the user UIDs which match those particular traits. And this is like a common thing which is used like almost everywhere. For Uber, like the issue was that we relied on a proprietary database before, and that database was costly to say the least. And we were like trying to figure out how to move away from it for quite a lot of years, to the point that I think when we ran out of all options and Pinot announced that there's going to be a multi-stage engine in Pinot, then we were like, let's try this out and let's invest a lot of resources on this. So that's what we did last year. We started working on it, and the key requirement for the use case was that we needed to do distributed joins. And obviously you want low latency because everyone wants low latency. And another thing which was a key blocker for us from migrating to other technologies that we have internally was that we wanted real-time data updates. And we're talking about like 1 million writes per second or something like that. So there's a lot of writes per second that you want to support, and you cannot afford to like have a very high lag in the writes. So yeah, those were the requirements. The scale was high. We didn't have any technologies internally. Pinot announced multi-stage engine. We thought, let's try it out. And yeah, I think there were like a lot of reasons like why we wanted to do this, but obviously the biggest one that comes out is that the dollar savings was like really, really huge. We have a Pinot team at Uber, so like having the same platform for everyone like means that you have a consistent support across all the technologies. So, but I'll talk about that in the end. Yeah, and just for context, like this is how things used to look like, and they still look like this, but Pinot could only support stuff like this. So we had scatter-gather kind of queries. So your broker is where your queries get submitted to. And the servers are where the data is. So the broker only does like query processing, query planning, and in the end, it also does a reduced step from all the servers. But this is what we had before. The servers would have the data, and let's say you have a query like select count star, city ID, blah, blah, blah. These will be run in the servers, and the counts and the grouping sets that you get out of the server, they are again reduced back in the broker. So you can return the right result back to the user. So this is what we had before, and with this design, you cannot support join queries. So there needed to be like some redesign of this system, and which is what the multi-stage engine did. And with the multi-stage engine, you can do stuff like this. So this is a query plan. Previously, I was just showing the server topology, but in the query plan, you can have any sort of complex query which is doing any SQL-y expressible stuff. So for example, in this case, this is like similar to the use cases that we have internally. So we have a riders table which has all the riders that are there registered at Uber with certain attributes like device OS, last trip they took, and other attributes. And we want to do cohorting on this. There is another table which is like the audiences table. So users are also allowed to create certain kind of audiences which might not fit the attributes that we have in this table. And they can import that using some tooling that we have internally. So someone could go to the UI and say, okay, I want this. My users are sitting in this particular table in Hive. and I want them to be ingested into Pinot. There is a streamlined process for it. We have a dedicated platform for it. That data ends up there in Pinot, and once it ends up in Pinot, now they want to see, like, I want to target users who match these particular traits and who are part of this particular audience UID that I ingested in the past. So, so yeah, it leads to queries like this. This is like an example. There is a bunch more complex queries, but the issue with the previous design was that we couldn't do something like this because this requires data shuffling. Like you cannot have a single server doing everything and just returning it back to the broker. Like you could implement it in certain cases and it would work in certain cases and blah, blah, blah. But in the end, you want to do it properly. You cannot be just like, oh, it works for this partitioned use case and it doesn't work for some other use case and for some other query pattern. So yeah, so the multi-stage engine fixed all of these issues, and this is what we were going for. This was our goal to enable. And just for like the scale numbers, I think you can take your time to like go through it, but we had a bunch of writes per second. We had really wide columns, which is not something we have had at this scale before. So this was also like something new to look at, like hundreds of columns in a table which is like doing hundreds of thousands of messages per second. And the tables themselves were like terabytes large. We have had terabytes large tables, but not like joins was obviously the first thing that we did. So this was like a new experiment. The joins were also large, like you have billion cross hundreds of million kind of joins. QPS was low, but the thing about like when you're looking at long-lived queries, I don't think like QPS is a good metric that you should track, but when you have flexibility on the latency of the query, I think you should be looking at from an engineer's perspective, you should be looking at the concurrency of the queries, because that is where you will probably saturate. Like if let's say you have 5 QPS and the queries are taking 2 minutes, in 2 minutes you'll have like a bunch of queries which will be running like, which will probably like outnumber your vCores per server. So you have to look at concurrency at that point and not exactly QPS. But yeah, QPS is a bit low, but it's consistent and the concurrency can exceed the number of vCores that we have. And we have super complex queries. The issue is that we have opened this to users, and users want to do whatever. So they will have like 10, 20 different audiences. They'll be like, I want users in this audience, but not in this audience, and in this audience, but not in that audience. And that immediately becomes like a query which has like 10 plus joins, which leads to 20 plus stages. And it leads to like all sorts of weird patterns and like scalability and other issues that you may expect to come. So yeah, obviously now that I'm giving the talk, we know that it works, but I'm just like setting the context, like why it was challenging to get it to work. But yeah, so, and another thing was that we wanted to support streaming like a lot of rows back to the user. And this was again something that we haven't done conventionally in the past. So in this case, like the requirement was that they want to stream billions of rows back to the user, because the users are interested in give me the user UID so I can run my marketing campaign. So just returning counts wasn't going to cut it here. So that was also something that added to the complexity. And yeah, the queries are dynamically generated. There's a very neat UI which like allows you to do like, I want users in here which are in this custom audience and will have these attributes. So the users are not writing the queries. The users are dealing with a very friendly interface. And the queries are dynamically generated. So which means like usually what happens with Pinot is that the queries are hard coded in your backend service. So it makes it easy to predict the query pattern and the query load. But with this kind of pattern, people can generate any sort of joins. So 1 hour you won't have anything. The next hour someone is running like billion cross 100 millions of joins, and you'll have a different performance altogether. So that was also one thing which added to the challenge of this. Apart from the fact that master was like Pinot master was like progressing at like 50 commits per week, and so that was also a bit of a challenge. But yeah, going back to the journey, so I'm starting with January because that is when let's say the heat turned on. Like if you thought this was hot, you don't know me in January. But the heat was really on because we enabled shadow traffic from our customer. And we essentially had 0% reliability. Everything was going down. Every 2 hours, the servers will crash. Memory was full. Ingestion lag was like 1 day, and the table retention was 2 days. So yeah, it was not a good time. And essentially, like the story was that we went on vacation like in December, as I think everyone does. And I came back and I looked at my Grafana dashboard. And I was like, what happened in that time? So the only thing that happened is that they enabled shadow traffic, and that brought up a lot of issues. And we had a strict deadline to make this work. Because of some internal reasons, like we had to get it running by worst case March end. So we had to make it work hook or crook. So, but the issue was that it wasn't just queries, like there was something going on in ingestion as well at that point, which we didn't know. So we had to start looking at our cluster and everything. And we had a really large cluster, so debugging, thread dumps, heap dumps, what have you, like, and yeah, the master is like progressing 50 commits a week. So that was the problem statement at that point, and I think everyone was questioning whether Pinot is going to work or not. I was also questioning it. I think if you were to like make people bet their money against it, I'm pretty sure everyone would bet it won't work out. But obviously, fine, it did. I'm giving the talk. So yeah, so we started by looking at. So I think there were like a lot of issues happening. So when there are a lot of issues happening, it becomes very hard to focus on what is exactly causing the issue, because if your server is crashing every 2 hours, like where do I start looking at even? Like so, the first thing we looked at was that the memory was going up even if I was like running 2-3 queries, or something like that, which suggested that there is something, queries are doing something which they're not supposed to do. Looking at the query, then we figured out that projection pushdown was not happening. So by projection pushdown, like in case you're not aware, like that essentially means that when you run a query like this one, like we have select count star from riders and so on and so forth. For the riders table, you need to do an index lookup on is online and country, and you need to read the user UIDs to do the join between the audiences table, but you don't need to read any other column. And the issue was that we had 100 other columns apart from these. So projection pushdown not happening means that we were reading all the columns. And this was a bug in like how we had wired the calcite optimizer and the SQL to rel converter. I worked with StarTree folks, and we figured out a fix for this, and thanks to StarTree like for merging it.
How did you root cause this? Like this is the issue, like you are reading extra columns also, and this is not happening.
Yeah, that's a good question, and I appreciate that you understand that it was a bit hard to figure out. But I think I ran a bunch of, so for every query I was running explain plans, so that was one thing. The other thing was that we had two regions like most people do, and we asked our users like run your shadow traffic in the other region. I'll use the other region as my test bed for everything. And I was running queries, explain plans, thread dumps, and I think it was in a thread dump I realized that there is a lot of time being spent in converting the columnar data to row-based data, and that's where I figured out that this is probably happening. But that's a good question, yeah. So yeah, I think this was an issue in like how we were using the optimizer rules. This was a desperate time to the point I think there was a Pinot issue as well, where I was having a discussion with Rong, and we were trying to figure out, at least I was trying to figure it out by asking ChatGPT, which is what you do in 2023. And it didn't help, just so, yeah, it was throwing us in like different directions altogether. So I think the approach that helped was like just download the Apache calcite code, look at every class and see like where the issue. I think this is like a startup opportunity if anyone is interested, but I think you have a code base, but it's very hard to figure out what solves your problem. It was just a single config in the end, but like figuring out like that it was a single config, especially for a complex system like calcite, was a hard thing that you have to go back and like once you know it, like it's obvious, but it's hard to discover it the first time. So that was something that we found out, and we found out like the fix for this. Like I think we can skip that. So yeah, that fixed the projection pushdown. The next thing we noticed was a lot of time was actually being spent by the scheduler. So the previous approach that the previous implementation of the scheduler was doing was it was trying to compute what are my next stages I can run, what are the next plan fragments I can run dynamically and synchronously. So, and that was very costly the way it was designed. So we rewired it a bit. We introduced some clean states about like in what states a given plan fragment can exist in. And we came up with a simple algorithm which was very efficient and which worked out for our clusters as well. And I think it's still that way. We have added like one more state to this to indicate the killed state. But other than that, it's pretty much the same. And yeah, the way it works is that it's a cooperative query scheduler. So as you might imagine, for a multi-stage query, you have different stages. Each stage will have its own operator chain, as we call it. So it's a set of operators that you run. And these are run in parallel. But most of the time, let's say your leaf stage is very costly, then your join stage or the non-leaf stages won't get any data. So they don't need to like occupy any thread or anything like that. They should yield the resources and let the other chains which are ready to take over and get scheduled. So that's what the cooperative query scheduler is. Like we have a state to indicate that a operator chain is available to run, but it doesn't have anything to run, which is the available state. The ready state is that you can just start running the operator chain right now. And the running state is when the operator chain is running and occupying a thread and consuming CPU resources and actually doing some work. So I won't get into the details of it, but like this also like got us a lot closer to. At that time, I was hoping for like even 90% reliability. For me is like an achievement, but we were hoping for 95% reliability. But this alone didn't get us there. We further found out that predicate pushdown wasn't working. For this one, the issue was that essentially, again, it was a calcite wiring issue. So how you configure your optimizer rules to run was a bit different than what it needed to be. And to explain this with an example, let's say you have a query plan on the left. In calcite, you have rules which look like filter project transpose, filter into joins, which essentially look at two rel nodes, which are the two relational nodes. And they'll compare their properties and they'll try to do push down, or they'll try to do merge them, or they'll do what have you. So that's how calcite rules are usually. But we were surprised is that how is predicate pushdown not working, because it is supposed to work. Every database is doing it, so something must be going wrong in our implementation. And what we found out was that essentially we were giving. So calcite has a heuristic planner which we use. There's also a volcano planner which is like a cost-based planner, but as far as I know, I think only Flink is using it. No one else is using it. But yeah, the heuristic planner essentially asks you to give it a set of instructions. And the planner essentially runs a program which will run those instructions one by one. And the issue was that either you could give all the rules as a single instruction, or you could give each rule as a separate instruction. And what we were doing was the latter when we found this issue. And what we needed to do was give all these rules in a rule collection so that they are run in a single instruction. Because if you run all of the rules in a separate instruction, what could happen is, let's say your filter project transpose rule is first, which essentially swaps the filter and project nodes. So it will push down a filter node past a project node. And your filter into join comes after that, so it pushes filter past join. Then if you have a plan like this on the left, which is a very common thing for anti-join queries, or like anti-semi-join queries, aka the not in clause. So in that case, this won't work because your filter project transpose won't be able to push down the red filter node. And your filter into join node will work, but you want the filter node to go down to the leaf stage. So yeah, that was the issue. So once you like run this in a single instruction, then the way the graph planner works in Heb program, like that takes care of like ensuring that all the rules are run together. So if one rule matches in one iteration and then the second iteration the other rule matches, both of them will be run, and there is no specific ordering that you need to give them. So that was another good learning out of this. And yeah, finally I think we found that there were like a bunch of leaks happening in the system. There was like a bunch of reasons for this. I don't think it makes sense to go into the details of those, but at a high level, what was going on is we have a kind of a volcano style execution. So each operator is calling get next block within a stage. But across stages, there is a push based mechanism. So for example, let's say you have a simple join query which has 2 child stages. The stages will run, since they're leaf stages, they'll start running immediately once you submit the query. But the join stage will yield and it will wait for the leaf stage to signal that there is some data ready. So once the leaf stage signals, okay, I have processed some data, there is a new data block coming in, the operator chain corresponding to the join node will like wake up and it will start executing and it will start pulling data from, not pulling data, it will start consuming the data that is already pushed by the leaf stages. So it's a hybrid of like pull and push based. So in case like you're interested, like you can read the Volcano paper, but there is also morsel based execution that DuckDB uses. That is also interesting, but it is not something that we use. And I think that as far as I know, it's a bit tricky to implement in shuffle based and distributed scenarios. Like DuckDB is like single node, as you might know already. And some other things that made it a bit more challenging than like your general problem statements is that we had like gRPC versus local data transfers, which have different semantics. For example, like gRPC transfer will be done through a connection, and the connection, the server doesn't have any control over it. Like someone else is sending me data. I can like start saying, okay, I'll add a handshake and I'll reject things and whatnot. When failure scenarios, even the receiver might not even know that there is a query like this coming in. For example, like it could be that my query is running on 4 servers, and the dispatch to one of the servers failed. And that server is now waiting for data from the other servers, and the other servers are waiting for data from that server. And they could like and continue to like hold resources for the entire query duration. So there's like nuances there which like make this like a bit more complex to fix. And the other thing that made it complex was that at that time, like we had a lot of push to go to higher reliability. So we were trying to like move fast, and our cluster was really big. So deploying, I had to deploy like over the night. In the morning, I'll see whether my patch is working or not, because the shadow traffic is like continuously running. But that's where the iterations also took a bit longer than they needed to, because this was only happening in cases where you have failures, where one client is failing out. You could say that you can implement this on a local level, which I definitely agree with, but essentially you need time to do this, which we didn't have. So yeah, that was also complex, but yeah, that is also fixed now. And yeah, so the next step was, there were a bunch of other fixes, but that pretty much got us to 95% kind of reliability. The next step was going from 95 to 100. So this was back in March, we were around 95%. And finally people were like, okay, this is maybe going to work out. We have to look at the last 5%. And we started looking into the other issues. Then we found out that our scheduler uses request ID, which is sent to us by the broker. And the request ID is a long which is incremented from 0. So obviously, like if we have multiple brokers, then they'll collide at some point. And when they were colliding, we were seeing like all sorts of funny issues. So it was throwing me into different directions. We were seeing like things like, okay, schema is not compatible between stages. I was like, this is definitely a calcite bug. I spent a day or a couple of days like trying to see like this should be a calcite bug. I should be able to fix it. The funny thing was that when I ran explain queries and other things, like I wasn't seeing any differences, but somehow it was happening at that point. And another issue was that for this cluster in particular, we didn't have log aggregation enabled. So, and the number of logs is just too much. Like where do you start even looking at it? So yeah, we finally figured out that it's because of these collisions, and we made a fix for this. This is also fixed in V1 now. V1 also uses the unique request ID. So yeah, this also fixed a bunch of issues, and this is an interesting one, especially if you are in DB research or anything like that. So essentially, for the partial upset feature, which Uber itself contributed, we get the requirement there is that you have a table, and again, let's say you have a Kafka topic. You don't have the full attributes every time. You have like only one or like a subset of them, and you want only those to like act like an update statement in general SQL. So the issue with this is that when you are applying the updates, like you have to read the previous row, which doesn't match with Pinot's columnar storage. Because if let's say I get one ingestion event which has 100 different columns, and I have to read the previous record, then I have to read like 100 columns, and the data is in columnar format, so I'm doing random reads on it. This doesn't play well with mmap, which is what we use. And these are like known kind of issues. Like Postgres also has this issue, but Postgres has the advantage that it is row based, so it doesn't like suffer as badly as this, but we did suffer a lot because of this. And the fix for this was something I think is a very ingenious kind of solution, which is we essentially like auto restart servers every 2 days. So there's a saying, right? We're not shipping fast enough, you're not auto restarting or restarting your clusters every few days. But yeah, initially I was doing it manually, so I had a alarm clock in my phone to wake me up every 2 days or so at a given particular time. I'll click on restart on my UI, and that's how things were going. Then I implemented the auto restart. Meanwhile, I looked into like other solutions as well, and there are some solutions to this which I won't get into right now.
So why is high TLB shootdown also a problem over here? I think that's like at the micro level, but it would be a bigger problem because you're reading like n number of rows for all those columns.
Yeah.
So will that have an impact?
Yeah, so the issue is that your CPU basically becomes useless because we are having like 200k messages per second ingested across a bunch of servers, which is without replication. With replication, it's like 400,000. Each record has like 100 plus columns. So, which means that we are doing like millions of random reads. And after a certain point, most likely because of memory fragmentation, this issue becomes really worse. Like if you let the server run for a couple of days, initially in the beginning everything would work fine, but after a couple of days or 3 days, like it will start having issues, and that's why we had to implement auto restart. So going back to the TLB shootdown issue, the issue with that is that it basically renders the CPU useless because our CPU utilization is going down to 10% or so, and this was like astronomically high. Like the TLB shootdown, I think they were happening like for every memory access because. As you may imagine, like whenever a query comes in, as Chinmay also mentioned, that let's say it has filters on 3 columns, you'll have to read those 3 indexes across a bunch of segments. And if each access is causing you a major page fault, that is like a lot of page faults. So, and this becomes worse with like NUMA systems which have like high number of CPUs. So, it essentially didn't align with like our expectations and design in the end. So that is something we fix with auto restarts for now. But I think generally speaking, you shouldn't have this issue because I think the issue with us was that we are running it at very, very high scale, which is not very normal. I think normally things should be fine. We actually had been running partial upset for a while in production, I think for around 8 months or so for I think 10 or 5 different use cases. Going back to, I think why we did this. So I think back when from January, I think in May we rolled out to production completely. By May end, I think we stopped writing to the proprietary database. In June, the license is expiring for the proprietary database, so I think we're finally free and we have completely migrated. There's a lot of celebration as well within the team, especially from the customers team. They also spent a lot of time and resources on this. So it was definitely a collaborative effort there. And StarTree, I think I would also like to thank here because they were also helpful in like working on solutions on most of the problems that I mentioned just now. So our latency expectation, so it depended on the queries because in some users are looking for like 100 UUIDs, some are looking for billion UUIDs. So the latencies could vary from like 1 second to minutes. And in our case, like we did see a significant improvement when moving from that proprietary system to this system. And we also had a very big reliability improvement. So we had like in Grafana, we had like really graphs running at the same time. So in Pinot, it will show the shadow traffic reliability, and in the other system, it would show the real reliability. And we were like outperforming consistently, and which was a surprise even to the customer team. I think they were surprised how fast Pinot is, which is something good. But yeah, we had like around somewhere around 99%. So this 99% is coming because the queries are dynamic. So unlike most analytical use cases, your data process is like interactive in a way. So it's more closer to interactive analytics as opposed to real-time generally when we talk about real-time analytics in Pinot. And I think the last thing I'll just touch upon is the technology consolidation, because that is a really underlooked maybe still. I think we keep on calling it out, but it's still very underlooked, because in a company, if let's say you have 5 different systems, you need 5 different support teams, you need 5 different types of expertise. But having just one like really reduces your costs long term. And I think Pinot is really helping us out there. And yeah, and just to close, we are adding some support. Some of the things we are still POCing, but I think hopefully you should see more PRs in H2. And yeah, that's pretty much what I had. If there's still any questions.